Welcome learners. In today's lecture, we are going to learn about the storage elements, and those are inductors, capacitors, and then we are going to see a concept of self and mutual inductance. So till now, we have talked about the basic circuit elements, and we know that there are 5 basic circuit elements. That was resistor represented by R, then we had inductor represented by L, then we had capacitor represented by C, and then we had the voltage source and the current source. So till now we have understood what is resistor and what is the purpose of resistance in a circuit. We have talked about the independent and dependent voltage and current sources, and in this lecture we are going into the domain of storage elements, and we are going to talk about the remaining 2 basic circuit elements, which is the inductor and the capacitor. In inductors and capacitors represented by symbol L and C, we are going to look at its terminal behavior. By terminal behavior, we mean that we are going to see what is the voltage and current appearing across the terminal or the ends of these 2 storage elements. And once we know, we can use these circuit analysis techniques which we saw previously, which is related to KCL and KVL, which we called as the Kirchhoff's laws, or we can use the node voltage and the mesh current methods to do the analysis of these storage circuit elements. So this is what we are going to understand in this lecture and the forthcoming lectures. So now let us see that what are the limitations that we had when working with resistors or the circuits that had resistors in them. So when we utilize the circuits having the resistor elements, we found out that resistor is a static element, and it is also passive in nature, which means that it cannot generate any energy, but it can become a source for elements or charges to pass through it. So resistor is called as an static element because it cannot store energy. On the other hand, the elements which store energy, in our case inductors and capacitors, these are called as dynamic elements. Dynamic elements because they can store the energy, and if we want, we can retrieve that energy. But keep in mind that they are also passive in nature. So these elements are also passive in nature, which means that they independently cannot act as a generating or a source. Rather, first they need to store energy, and that stored energy is then retrieved in the form of generation of energy. So these 2 elements, inductors and capacitors, are passive in nature. Now when we are dealing with the dynamic elements, another thing comes to us, and that is the complexity, or we can say the mathematical complexity in solving these elements, which means that we have to go into the domain of differentiation and integration to find a complete solution to these storage elements, which we are calling dynamic elements. And another thing that we are going to encounter in these 2 elements, which we are going to later study in our upcoming lectures, is the steady state and the transient state. So another thing associated with these energy storing elements is called the steady state condition, and the second one is basically the transient condition. Obviously these things we are going to discuss in the upcoming lectures, but in this lecture we are just going to concentrate that what is an inductor and what is a capacitor and what are the properties and what is the working principle behind these 2 elements. So let us start with introduction to inductors and see some historical aspects and its working. So we talk about introduction to inductors. So let me take you back to 1820s, start of 19th century or the mid 1820s, and there was a Danish scientist called Hans Ørsted. You might have read about these things in your lower physical classes or physics class, but anyhow, just to revive your or jog your memory. So it was the era 1820 where a Danish scientist, Hans Ørsted, was basically studying about the flow of currents in inductors, flow of current in conductors. So during his experiment, he was intrigued by the fact that what happens or what other parameters are there if we take any wire, let's say a conductor, and a current is flowing through it. What are the effects or the analysis happens when a current is flowing through a conductor or a piece of wire. During his experiment, surprisingly, he kept this wire next to a compass. So the compass has its north and south. So let me call this as a compass. Now, people at that time knew that electricity and magnetism existed, but they had no clue that they are correlated to each other. They were being analyzed separately. So when this scientist placed this piece of wire close to this magnetic compass, he saw that the pin was deflecting. So sometimes it moved to the right, sometimes it moved to the left. And this intrigued him that why is this happening? Because people knew, and we know now, that a magnetic compass basically generates its own magnetic field, so which is moving the needle with reference to the magnetic field generated by the earth. So why this happened, that when this piece of wire carrying current was brought in close vicinity to this magnetic compass, the deflection was happening. So he did some analysis and figured out that this piece of wire was indeed producing its own magnetic field, and thus the magnetic field of both the elements were interacting, and that's why the compass needle was deflecting. So this was the first instance when the scientist came to this conclusion that electricity, or let me use a simple version, that electricity and magnetism are correlated, or one is able to generate other and vice versa. So this was the first time that these two elements were considered to be a part of each other or associated to each other. Later on, this theory got verified when another scientist, a famous one known as Michael Faraday, was also working on the concept of electricity and magnetism, and he also verified Hans Ørsted's theory, saying that this phenomena is true because what Faraday was doing, and we know by his famous electromagnetic force equation or EMF equation, which you might have heard, is stating that EMF is basically equal to minus n d phi by dt. Now this is the famous equation which Michael Faraday proposed, where it is saying that the change of magnetic flux, so this is the magnetic flux, let me use a different zone. So this is the magnetic flux is basically changing, and this is the number of turns. So number of turns which will produce an electromotive force, or which we called as an induced EMF. So this is the mathematical equation that Michael Faraday proposed. And what does it mean? So it means that what Michael Faraday did was that he took a piece of wire and he passed a current through it, and based on the Hans Ørsted's theory, this electric current will produce its own magnetic field surrounding it. And thus we also know by the right hand rule that if the current is flowing in the upward direction, then the magnetic field will produce when we curl our finger. So what he did is he took a piece of wire where a current I was flowing through it and a magnetic field is produced around it. Now what he did is he brought another wire close to the vicinity of this wire. So let's say this is another wire. Now the second wire shown here in red is not energized, it is not provided any sort of voltage. As soon as he brought this wire in vicinity to this black wire, he saw that certain amount of voltage was induced in this wire, although the second wire shown in red was not being energized or was not provided with any external source. So this was intriguing to him, and thus this phenomena, which also verified Hans Oyster's theory, was mathematically represented by Michael Faraday in this electromotive force equation. So what Faraday said is that induced voltage is produced by the magnetic field produced around the wire shown here by the black wire. But there is a condition to it. The condition is that this induced voltage V is only produced as long there is a changing current. So as long we have a time varying current, let's say di by dt, this time varying current is going to produce a time varying magnetic field, and then this is going to produce the induced voltage. So this is the condition, that in order to have this induced voltage, you need to have the current that is changing with regards to time. So this is what the Michael Faraday proposed, and this is how we got our EMF equation. Now how this relates to the inductor, so we are going to look into this. So what is an inductor? Just to put something into perspective. So if you consider a single piece of wire, let's say if I have a single piece of wire, and we know that ideally its resistance is 0 ohm, which means that the voltage across this is 0 volt and the current can easily flow. So we say that this is a short circuit wire if these two conditions are met. So this is a short circuit wire. Now what we can do is we can take a piece of core, let's say it's any cylindrical material, and we now take this wire and we start wounding this wire across this piece of core. So now this is what we get. Now our wire is basically, so let me get this right again. So this piece of wire is now wounded, or we make it as in this form. Now the piece of wire gets this shape. So now the wire, which was straight, has turned into a coil. So now when this phenomena happens, we introduce the element which is called as inductor, represented by symbol L. So here you can see how this thing is appearing. So inductors are basically designed from a simple piece of wire, but there are few conditions which get changed, and we are going to talk about that. So first let us look at this inductor. So as I mentioned, inductor is a passive element, and they are basically used in high power systems, electrical machines and electronics, but in our course we are just going to see an introduction of this inductor. So how this is made? We just take a simple piece of wire and you take any cylindrical material. So this is the core which I drew, which I was talking about. This core can be magnetic or non-magnetic in nature, and when you wind this wire around this core, you make this certain coil form of a shape. Now this coil is basically what we call as an inductor. Now practically inductors are not readily available, so you can make your own coils. So practical inductors might have different forms. You can see they come in the form of rectangles, they can be circular. These are different variations that are used in small electronic projects or power electronic systems, but this is how a inductor looks like practically, and you can make your own conductor because it is just a simple copper wire that gets wound around a cylindrical element. It can be a square element as well, you can see over here as well. So this is how conductors are made. Now once this is made, what are the things that apply to the single wire is not applicable to the coil? So as I mentioned, that if you have a single wire, we say it's a short circuit where the voltage comes out to be 0, but in case of coils, this principle of voltage getting equal to 0 is not applicable, which means the Ohm's law is not applicable. Although the resistance is ideally 0 ohm, but the voltage is not equal to 0. And this is happening why? Because this is due to the Faraday's principle and the principle of magnetic field generated by the flow of current. So consider it in such a way that if I have this coil which is made up of a conducting material, and the principle is called self-inductance. So let's say this is terminal A and this is terminal B. Now what is happening? Let me use a different color. So let us say if the current is moving inside this wire, we know according to Hans Oester's principle, and later on it was refined by Ampere's law, that magnetic field is going to produce around these coils. So the flow of current, let us say for the first, so if the current enters this first coil, it is producing its own magnetic field. Then this current keeps on moving, it is going to go to the second, and this is going to produce its own magnetic field. Similarly, when the part of the current enters the third coil, it's producing its own magnetic field. Now what is happening? Now since the magnetic field is produced in this coil, it is going to induce a voltage as well over here, and this process is basically the self-induction, which Faraday was explaining in his principle when he brought this wire shown in red closer to the black wire. We saw that the voltage was induced. So the same principle applies to these coils individually. So every coil is producing its magnetic field, which in turn is producing a voltage here. Then this is again going to produce a voltage over here. Again a voltage is going to produce for this portion. Again a voltage is going to be induced over here. So this is the process of self-induction. And again, since resistor tends to be 0, but Ohm's law is not applicable in these kind of storage elements. So this is what I was trying to explain earlier, that although for a short circuit the voltage should be 0, but in case of the inductor where we turn a wire into a coil, the voltage is not going to be 0 because the induced voltage is produced based on the principle of the electromagnetic interaction presented to us by Ampere's law and Faraday's law. So this is how an inductor basically is operating. So the main equation that we get after all this discussion is this, and let us further refine the definition of an inductor. So if I want to define an inductor, I can say its definition so inductor is an electrical component that opposes the change of electric current So this is what an inductor is, if you want to define it in a traditional way. And what is the change or the opposition of electric current, we are going to see shortly. So mathematically, what the inductor is doing is basically it is inducing a voltage. So we can write it in such a way that the voltage induced is basically directly proportional to the change of current. Again, remember, this induced voltage is only produced when we have a changing current. If there is a direct current, there is going to be no voltage, and we are going to look into that. So if there is a change in current, we get the induced voltage. If we further simplify this equation to get rid of this proportionality sign, we say that voltage is equal to L multiplied by the change of current, and this is the equation which is very important to us when we are talking about inductors. So whenever we have an inductor placed inside any electrical circuit, we are interested in finding the voltage induced by it, and the equation 1 basically represents the mathematical expression of working of an inductor. Now in this equation, we know that di by dt is the change of current which produces the induced voltage. But what is this L? So this L is basically the inductance of the inductor. Since this is similar to the resistance of a resistor, so this is inductance of the inductor, and this is the inductance which is basically responsible for opposing this change of this inductance L opposes the change of electric current. So this is the term that was mentioned in the definition. Now this inductance, what is this? So it depends upon or mathematically we can say that inductance depends upon the material property represented by mu, the number of turns of the coil on any material, the area of that coil, and the overall length of it. So this is how we find the inductance of the inductor. So what are these parameters? Mu is basically the material property. So I can say that mu is the material property. We call this as permeability. So material property, you might have heard about this in free space. Mu naught is 4 pi into 10 raised to power minus 7 Henry per meter. So this is again the property of free space. If you use any other material like an insulator or a magnetic core, then the property of mu will change. Now where are these things? So if you look at the practical, take any of this material, okay, let us say this. So we can calculate inductance that this is going to be the property mu, this is the number of turns, this is the area, how much turns it is covering, and this is the total length of the material. So this is how the inductance is calculated when you wound a wire on any cylindrical or a rectangular or a circular material. So this is basically material property for free space. This property changes based on the material, and this is how you calculate. N is basically the number of turns of the coil on any material. A is the total area of that material, and L is the total length of that material. So this is the parameters of finding the inductance of the material, and this inductance which basically opposes this change of current in the voltage. So this is the relevant equations for these two materials. The important being equation 1, where we find the induced voltage, and how you can find the inductance. It is represented by, let's say I call this equation number 2. Okay, now what else can we learn from this equation? So before moving into the equation, we need to know the symbol of inductance. So normally, practically, inductors look like this. Obviously we cannot use this in our circuit analysis. So the symbol of inductor keeping in mind the current direction and everything. So the symbol of the inductor is basically a coil which looks like this. This is L. We can say this is the voltage appearing with respect to time, and if there is a current flowing through it, we are going to say it is changing with regards to time, because induced voltage depends upon the change in current. Mathematically, then if we follow the passive sign convention, then for this symbol the equation will be such. But if we change the direction of the current to, let's say now the direction of the current is in the opposite side, which means we are entering from the negative terminal and leaving the positive terminal, passive sign convention, then the equation of inductor comes out to be minus L di by dt. So this is for the negative one, and other is the original one if the current is entering the positive terminal by default. So this is based on the passive sign convention. Okay, now what do we understand or extract more from these two equations? So especially from equation number 1, there are two things that are very important for us in understanding the working principle of inductor. So from equation 1, so this is the equation, basic equation for the inductor, and what we can see from here is 2 points. The first point is that we know that this equation is basically representing the voltage across the inductance as a function of current. So we note that the time or rate of change of current, the time or the rate of change of current is responsible for induced voltage. So as long as there is a change of current, we will get an induced voltage. However, if the current is constant, if the current is constant, which means the current is not changing, it is like a DC source current, then the induced voltage for inductor will be 0 volt. In this case, now the Ohm's law is applicable, which means our coil is going to act as a short circuit element, which means it will act as a normal wire. So this is the first condition we need to remember when looking at this equation of inductor, that the rate of change of current is responsible for producing this induced voltage. But if the current becomes a constant value, which we say as a DC source, then the output of this voltage will be 0, and thus we go back for this inductor to be working as a simple short circuit wire. The second important point for inductor is that this change of current, although the current is falling, this change of current di by dt, so let me put it as di by dt, shouldn't change abruptly. So the change of current shouldn't be abrupt, or it shouldn't change its value instantaneously, or to put it very simple, we shouldn't disconnect the inductor from any circuit suddenly, because if we do so, then the voltage will go towards infinity. Because let's say if the value of change of current was 5 amps and we suddenly brought it to an infinity or a higher value, let's say infinity ohms, then what is going to happen? The voltage will go towards infinity, because voltage is directly proportional to the rate of change of current, and this is not allowed. This is not allowed when we are working with inductors. We have to avoid this phenomena of suddenly disconnecting the inductor from our circuit, because this condition where the voltage goes towards infinity is basically we are making our circuit to be an open circuit condition, and in reality, to provide an infinite voltage, we need to have a source that is giving infinite power, and that is not physically possible. So please remember the second condition, that inductors, although do provide the induced voltage by the change of current, but the change of current shouldn't be instantaneous, or it shouldn't be abrupt. It should gradually change its value so that we can get the induced voltage. If we don't do this, we are going to create an open circuit condition, which means that the voltage will be infinite, and to have this infinite voltage, we should, or we are assuming that the power is infinite, and it is not possible. Practically, we don't have an infinite voltage source. Another thing associated with this thing is that sometimes, but not in most of the cases, in small electronic projects or conditions or devices, we may use this open circuit condition by a principle which is known as arcing. Again, this topic is mostly explained when you study the course of power electronics, but what is arcing? So arcing is a phenomena that we can utilize for some of our small voltage equations, but for higher cases we avoid this. You might have seen these phenomena in your transformers whenever a high voltage wire gets disconnected. So let's say this is a high tension wire and it has got disconnected from its transformer. So this is the wire that has got broken. So this was, let's say, my transformer with a coil, and the wire got broken. Now whenever this wire gets broken, you might have seen some form of electric sparks. This form is known as arcing, and this is a phenomena that is very dangerous, because you have suddenly disconnected the elements and the inductors placed over there had moved from the short circuit condition to an open circuit, and this kind of phenomena is known as arcing. We sometimes utilize this in the process of, you might have seen spark plugs in your vehicular engines like your car, your motorbikes. So the spark plug basically also works on the phenomena of arcing, where you ignite your car or you start your engine by using this phenomena of arcing. So sometimes we can utilize this process to our benefit, but in most of the cases, as I mentioned, that inductors are used in high power systems, so we try to avoid these kind of sparks which may lead to damaging our system. So that's why we never keep our inductor in the open circuit condition. We always tend to keep it in the short circuiting or at the minimum possible levels where we can control this arcing phenomena. So please do keep in mind these two important conditions. Now let us take an example and further understand the importance of these two conditions so that these two conditions are well molded into our brain. So let us take an example and see what we can further do with this phenomenon. So let us take an example and further understand these two conditions and why the voltage has to be taken care for, and we don't want this to be in the open circuit condition. So let us say I have this representation of the flow of current with respect to time. So this is a current that is changing over time. So this is a scale of 1, 2, 3 and 4, and let us say I take it to -1. So this is the behavior of the current, and after a certain time it becomes like a constant. So this is my I of t on the vertical axis and time is on the horizontal axis. Now I need to find for this given graph the induced voltage. Okay, so we know that the induced voltage for an inductor, so this example is associated with analyzing the inductor. So let me put it like this. Okay, so in order to find the voltage, we need to know the inductance and the rate of change of current. So let us say for this example, the inductance value is 3 Henry. Okay, so now we know that the value is 3 Henry, Henry being the unit of inductance. So how can we find di by dt? Okay, so we need to go to the graph. We can see in the graph that this is the slope where di by dt is changing. So this is the change of current. After point 0 till 4, the current is constant. So this is the constant current that we have in this vicinity. From 0 to 4, the current is constant, but this slope is from -1 to 0. So we can find the change of current using the equation of slope. And we know that for equation of slope, it is y2 minus y1 divided by x2 minus x1. Here y2 being this point, let us call this as point 1, y1 at 0, x2 let us say this point at center, and x1 is -1. So if you put the value 1 minus 0 divided by 0 minus -1, it comes out to be 1 ampere per second. So this is the change of current that we got for the slope. Okay, so this is 1 ampere per second. So if we put the value over here, then it comes out to be 3 multiplied by 1. So this is 3 volts. So this is the voltage that we are having. So for the voltage at this point at the slope, we are having the value of 3 volts. Okay, then this is good. So if you want to draw this, we can draw this exactly. So the voltage graph corresponding to the current graph comes out to be, so this is the time axis, and from 0 to -1 we get the value of 3 volts. So this is the value. So this is the under the curve, this is all 3 volt. Now what happens when we look at the current graph moving from point 0 to point 4, and we see this is a constant current. So whenever we have a constant current, so let's say then this equation di by dt is equal to 0 volts. So which means that this point is going to be 0 volts, because we know from the first condition says that whenever we have a constant current, the voltage comes out to be 0, and hence we have seen mathematically that from this point onwards, from 0 to let's say 4, this inductor or this inductor is behaving like a simple wire, because voltage at this point is 0. But before 0 and -1, we are getting a certain voltage of 3 volts. So the first condition is being observed over here. Now let us talk about the second condition. So in order to understand the second condition, let me use this space and see what happens with the second condition. So for the second condition, we say that the current should not be abruptly changed. So for the second condition, let us again draw the current diagram flowing through the inductor. This is I of t. But this time around, let us say that there is a drastic change in the current So previously we had the values of 1 or from -1 to 4, the ranges were from -1 to 4. This time around let us drastically change it from -1 to -0.1 and let us take this to 0.3. So now you can see the current value has been drastically changed and the behavior remains the same. So it has a value of 1 till this point, and after that it becomes a constant line. So now let us find the voltage. So the voltage is equal to L di by dt. We know the value of L remains 3 Henry, and now what is di by dt? So we need to know the value of di by dt at this slope. So if we go back to the slope and equation of slope, so the equation of slope, if I focus on this, it comes out to be y2 minus y1 divided by x2 minus 1, and it comes out to be 10 ampere per second. So this slope is basically having a current of, this point is basically having a value of 10 ampere per second. So from minus 0.1 to 0, the value is 10 ampere per second for the current, which means the voltage comes out to be, so V of L then comes out to be 30 volts. So this is the region of 30 volts. If I draw this, so this is the voltage graph, comes out to be, this is V of t from minus 0.1, this is 0.1, this is 0.2, this is 0.3. So the point comes out to be 30 volts, and you can see the voltage has been drastically increased just by only changing the current value. So in previous example, the range of current was from -1 to 4, or let us focus in this range, that the range of current was from -1 to 0. We got the induced voltage to be 3 volts. As soon as I drastically change the value of current from -1 to -0, the voltage has increased from 3 volts to 30 volts. So the voltage has increased from 3 volts to 30 volts. So this is the sudden change that we want to avoid, because let us say if I further increase the voltage from -1 to any other value, so what we are going to get is, let's say the voltage here then will reach a value of infinity volts, and this is the open circuit condition that we want to avoid. So hence we need to remember that the voltage shouldn't be drastically changed, because we are going to have an infinite voltage against the current that was drastically changed. So this is the second condition that we want to avoid, which is the sudden change of current, and the example shows this extremely well. Hope these two conditions are clear for you. Now let us go back to this equation and see if we have the voltage, can we find the associated current for it? So because we are dealing with current, so if we have the equation of inductor as L di by dt, so we can simply find the equation of current. We know that if something is integration, differentiation, its opposite is integration. So the current which is passing through the inductor is basically represented by 1 by L minus infinity to t naught V of t dt plus 1 by L t naught to tau ot V of t dt. Now this equation number 3 is another equation where we can find how much current is flowing through the inductor. We know that the voltage is present due to the change in current. If you are interested in finding how much the current is getting changed when it is passing through the conductor or the inductor, so this is the important equation that we are going to use. Again, more on this equation or discussion on this will be in the later lectures, but the thing to note over here is the first part of the equation and the second part of the equation. So the first part of the equation is known as the initial current. So this is the initial current, which we can replace it with I t naught, and the second part of the equation is the instantaneous current, which is basically creating the induced voltage. And again we have to be careful that this instantaneous shouldn't be abrupt. So this initial current, basically I naught, comes out because whenever we are dealing with storage devices and we need to solve them, So we basically need to know that what was the previous value. So if we simplify this equation, this comes out to be I T naught initial current plus 1 by L T naught by T V of T dt. So this is the final equation that we use when solving the inductors or finding the currents for the inductor. Again, I T naught is the initial condition or the initial current that was already stored, and then the next portion of the current is the instantaneous current which we are interested. So this is the equation that we use, and we are going to discuss on this in the upcoming lectures. But at this point, we need to remember that whenever we are dealing with the storage devices, whether they are inductors or capacitor, we always take care of the previous current or the initial current, and then we talk about the current instantaneous portion of the current. So this is the mathematical expression of finding the current of the inductor. And now coming to another two concepts, obviously we are talking about the energy storage. So what is going to be the energy stored in this inductor? So the energy for inductor, let us represent it by its symbol L. So we know that energy is nothing but the integration of power multiplied by the time, or we say that P dt. Let's put it in this way, 0 to t, P with t. So power multiplied by time. So what is the power in this case? We know that power from Ohm's law is the product of voltage into current. We know that voltage for inductor is L di by dt. You multiply it with current and you input it over here. So the energy stored in an inductor comes out to be half L I square. Again, you can do the integration. Not at this stage, we are not interested in the solving the integration. We just want to know the mathematical expressions associated when working with inductors. So the energy of the inductor, if you want to figure out, is represented by half Li square, and again the important element in this equation is the flow of current. So the current needs to be flowing and changing with time if you want to find the energy and power of this inductor. So this is all about inductor's energy. Now let us see what further we can do in terms of the circuit analysis. So say as we saw with resistors, that whenever resistors are available in a combination, how can we simplify those? We talked about in those lectures about R equivalent. Similarly, we are going to talk about the series and parallel combination when we have multiple inductors in any given electric circuit. So if we are going to talk about the series and parallel combination of inductors, so the principle remains the same as was for resistor, because we know that if the inductor is working in a short circuit, it behaves as a simple wire. So for series combination, let us say we have an independent voltage source V of S, and it is connected to multiple inductors in series. So this is L1, this is L2, and this is L3. We know the voltage appearing across is VL1, VL2, and VL3. So how can we solve this series combination of inductors? The basic idea is to apply the KVL on this. So if we apply the Kirchhoff's voltage law, we know that V of S is equal to VL1 plus VL2 plus VL3, and V of S is we know that for a series circuit the flow of current remains the same. So the flow of current remains the same, so I can write it as L1 dit by dt plus L2 dit by dt plus L3 dit by dt. So if the current remains the same, I can take it as a common factor and I will be left with L1 plus L2 plus L3, and we call this term as L equivalent. So for an inductor connected in series, we can simplify these three resistors into an L equivalent, which will be the sum of L1 plus L2 plus L3. So this circuit gets simplified to a simple voltage source connected with a single inductor, where its value is L equivalent and its voltage will be VL equivalent with the current flowing as I of t. So this is how we simplify the inductors connected in series where the equation resembles the same to that of a resistor. And if you remember, for the resistor connected in series, its R equivalent was R1 plus R2 plus R3. So this is the similarity which I talked about. What about inductors connected in parallel? So for parallel combination, again it is going to follow the same behavior as we saw with the parallel resistors. So for parallel combination, our circuit will have, let us say we have this current source I of S, it is connected to inductor L1, second inductor L2, let us say we have a third inductor L3. So for parallel combination, we know that the current gets distributed. So this is going to be a different current, but the voltage remains the same. So if I apply KCL on any of the node, I can get the equation as IS is equal to IL1 plus IL2 plus IL3, and let us write the simplified equation will be 1 by L1 plus 1 by L2 plus 1 by L3 followed by the voltage equations. So it is going to be V of t plus the initial condition for 1, initial condition for 2, for the second one, plus initial condition for the third one. So basically I am using the equation of current. What is the equation of current? This is the equation which I am using, right? So this is the equation of the current that we are using for the parallel combination. And finally we again get that 1 by L equivalent is equal to 1 by L1 plus 1 by L2 plus 1 by L3, and the rest of the equation remains as it is. Since we want the equation to be a whole number rather than the fractions form, so we say that L equivalent is equal to L1 plus L2 plus L3, or again the other rule that we always remember, that if we have two inductors, so we are going to write it as L1 L2 divided by L1 plus L2, and this is the same principle which we saw for resistors connected in parallel to each other. So this concludes our today's lecture on introduction to inductors, which was acting as an storage element. If I summarize the point that we have studied for inductors, so summarizing the points, it will be, the first point will be that it is an inductor is represented by symbol L and its unit or its units is Henry. Second, it is a storage element. This is a storage circuit element, and the storage is happening magnetically. Main thing associated with inductor is that it produces induced voltage which is dependent on the inductance and the rate of change of current. This is very important. The di by dt, rate of change of current, is very important because it governs how much induced voltage is produced. And then we have two conditions associated with this. The conditions being that if there is a constant current source, let's say a DC current, then we have a short circuit voltage, and this acts as a simple short circuit wire, and we have to avoid the abrupt change or abrupt change of current, because this leads to voltage becoming infinite, which is an open circuit condition, which means that it can make our devices faulty and the sparks may appear, which we called as arcing. So this is an important aspect. And then we saw the series and parallel combination of inductors. Again, they follow the same principle. So L equivalent is following the same principle as R equivalent, which we saw in our previous lectures. And that is the summary of today's lecture.